born on 3rd October 1923. In recognition of his valuable contribution, we are celebrating a year-long birth centenary starting from 3rd October 2022. We had a grand inauguration on 3rd October 2022 at the Vijnan Auditorium. Now we have Professor Prem Krishna and Professor A.R. Santakumar, who had a close professional association with him, to celebrate the event with us. To begin the event, I request our director to preside over the function and give a welcome address.
Thank you, Satish Kumar. It is my honor and privilege to welcome Professor Prem Krishna, Distinguished Structural Engineer and Emeritus Professor, Indian Institute of Technology, Roorkee, and Professor A.R. Shantakumar, former Dean and Professor of Structural Engineering, College of Engineering, Guindy, Anna University, and Emeritus Professor, Indian Institute of Technology, Madras. Welcome, professors, and also I welcome Professor Shekhar and Dr. G.S. Parani, Dr. Raja Shankar, Dr. Satish Kumar, Chief Scientist, and Dr. Bharat Kumar, Advisor, and R.D. Satish Kumar, who are here with me in this hall, and invitees who have joined virtually, my dear brothers and sisters of this campus. Ladies and gentlemen, Vanakkam, Namaskar, and good afternoon to all. Today we have gathered online for the first lecture series in connection with the birth centenary celebration of Professor G.S. Ramaswamy, founder director of CSIR Structural Engineering Research Center. As we all know, civil engineering is the way of life. It is all about planning, teamwork, experience, and preparing for the unexpected. Structural engineering is the art of using materials, but we know the properties which can only be estimated, to build real structures that can only be approximately analyzed, to withstand forces that are not accurately known, so that our responsibility with respect to public safety is satisfied. Structural engineering deals with the application of scientific knowledge to develop and improve infrastructure such as buildings, bridges, dams, roads, railways, and common utilities. Therefore, role of structural engineer exists in every walk of life. Infrastructure is the backbone of any nation's economy. It is important to provide structures and utilities to be safe, while solutions need to be environmental friendly, efficient, as well as economical. CSIR Structural Engineering Research Center was built upon the far-sighted vision of Professor G.S. Ramaswamy with an aim to have self-sufficiency in structural engineering skills, and was established on 10th June 1965 as a national laboratory under the Council of Scientific and Industrial Research. Professor Guruvayur Subramaniam Ramaswamy was born on 3rd October 1923. GSR, as he was fondly addressed, had his early education in Trichy and obtained his BE degree with honors from College of Engineering, Guindy in 1944. He then traveled to USA and joined the California Institute of Technology and earned his MS as well as CE degrees in 1948. On his return from USA, he was appointed professor and head of the Department of Civil Engineering at the Annamalai University, Chidambaram, when he was only 26 years old. He served as professor in the Department of Civil Engineering during 1948 to 56. Professor GSR initiated an early research on pre-stressing systems by guiding a postgraduate thesis on pre-stressed segmental stone beam in the year 1954 in Annamalai University. And this beam consists of 19 number of granite stone blocks with a drilled hole of 125 mm diameter. And the thickness of each block was 110 mm with mortar thickness of 25 mm. And the reinforced concrete blocks were equal to the depth of the beam was provided at each end. Trussness anchorage consisting of male and female conical wedges were used for force tensioning. Trussness system used for force tensioning was brought to the laboratory from the nearby Kollidam River Bridge construction site. This stone beam is still preserved as a monument in the Annamalai University in memory of Professor GSR. The ME student who did this thesis is none other than Professor Srinivasa Gopalan, who later served in Tyagaraja College of Engineering as professor and then as special officer and Dr. MGR Educational and Research Institute. And 2-year postgraduate course in structural engineering was introduced for the first time in the country by Professor G.S. in the year 1953 at Annamalai University. And in 1958, he joined the Building Research Center, Roorkee, as head of structures division and founded SCRC at Roorkee on 10th June 1965 and later moved to Chennai in 1974. Shell was his passion, which can be observed in many of the structures in our campus. Popular twisted reinforced bar or grip bar, which he took patent with Sri Sakarya Jad. Hard and untiring work is with intelligence was GSR's motto. And this grip bar technology was licensed to Tata Iron and Steel Company for commercialization. This technology also received the Import Substitution Award. This fetched a huge amount of royalty during the year 1970, and cumulative royalty for this single license between 1970 to 84 amounts to millions of rupees. And he established a number of disciplines and testing facilities in this campus. This is the far-sightedness vision of GSR. And he served as UN Chief Technical Advisor to Government of Trinidad and Tobago, and UN Advisor to Government of Iraq, UN Advisor to Deputy Minister of Transportation, Saudi Arabia, and visiting professor at University of West Indies and University of Arizona. He has authored 3 notable books, Design and Construction of Concrete Shell Roofs, and it is considered as the classical reference on shell roof all over the world. He was an excellent speaker, great orator, and prolific writer, and was always keen to learn new things. And he was recipient of many awards, which include Invention Promotion Board Award and Shield, elected Fellow of Indian Academy of Sciences and Indian Academy of Engineering in 1972. So his life was full of untiring activities. Even a few hours prior to his passing away, he was preparing notes for his next technical book. So my dear brothers and sisters of this campus, a person with far-sighted vision has founded this campus, and it is our duty to pay our tribute to the great man by keeping the campus vibrant with our outstanding scientific contributions. And once again, I welcome you all for this first lecture series in connection with the birth centenary celebration of Professor GSR. And I thank Professor Prem Krishna and Professor A.R. Shantakumar for immediately accepting our invitation. And we are fortunate to have both of them. Professor Prem Krishna, Doyen in Wind Engineering, and Professor A.R. Shantakumar, Doyen in Earthquake Engineering, which these two are very essential as we grow vertically, our construction grow vertically higher. And I would like to conclude with the Tirukural, Enniya Enniyangu Eidi Einiyar Tiniyaraga Perin. ஒன்றை செய்ய நினைப்பவர் அதை செய்ய முடிக்கணும்ன்ற மன உறுதி இருக்கும்போது அதை அடைய நினைக்கிறதெல்லாம் அவர் அடைவார். Which means that if those who have having the firmness, they will obtain all they have desired. And with this, I would again welcome Professor Prem Krishna and Professor A.R. Shantakumar. Thank you, professors, for accepting our invitation.
Thank you.
And we are eager to hear from you.
Thank you. Now I request Dr. J. Radhashankar, Chief Scientist and Head SHRD, to introduce our Professor Prem Krishna.
Yeah. Thank you, Satish. Very good afternoon to all, and particularly Professor Prem Krishna, Speaker of the Day, and Professor A.R. Shantakumar, and Professor Shekhar, who is in the audience, and Dr. Andavalli, and my other colleagues in the stadium, in the boardroom, and as well as otherwise, who are eagerly waiting to see the lectures. And Professor Prem Krishna is not new to this audience, though he has been a regular visitor to SCRC on many occasions. And I myself had the opportunity of introducing him in 2019. I hope you remember, sir, to give a motivation lecture.
Yes.
Now it's again my privilege and pleasure to introduce Professor Prem Krishna. Of course, I have a sort of a brief biodata, which Professor Prem Krishna calls as brief. But I can say one line as he's a friend of SCRC, friend, philosopher, well-wisher of SCRC. And then I'll come to the brief as the occasion demands. Professor Prem Krishna was born in March 1938, and he got his early degrees, bachelor's and master's in engineering from University of Roorkee, which is now called as IIT Roorkee. In 1961, he completed his master's. He got his doctorate from Imperial College London in 1964. Subsequently, he joined as faculty of civil engineering at IIT Roorkee or University of Roorkee. In 1965, the very same year, SCRC was started or inaugurated by Professor G.S. So a very apt talk will be there today by Professor Prem Krishna, rekindling the memories of Professor Prem Krishna. And he retired from the University of Roorkee or IIT from 1998, but he still maintains his contact till 2007, I think. Subsequently, in between, Professor Prem Krishna got his teaching assignments at the University of Illinois, Urbana, USA in 68, 69, and further at Imperial College of London, UK during 1969 and 70. In addition to his R&D, in addition to his teaching activities, he's also been active in R&D as well as industry interaction, particularly with steel structures, long span bridges, and wind engineering. That's what I could see from his career. Coming to the professional or membership positions, foremost is a fellow of Indian National Academy of Engineering from 1987 onwards. And it so happened that 1987 and INAE was established. So since establishment, he is a member, is a fellow of that body, and also a vice president of that INAE during 2018 to 2013, 2008 to 2013. He's also a founder president of Indian Society of Wind Engineering during the period 93 to 2000. Again, he's the president of International Association for Wind Engineering during 1991 to 95. And with CBRI, Roorkee, he has been a chairman of the Research Council during 2010 to 16 for 6 years period. That's all about the professional. And coming to the awards, primarily, I think he's a presidential award in recognition of his career for long contribution to wind engineering. It was given in 2021, and it so happens that only 3 people have got in this world so far, and only one from the India. He is Professor Prem Krishna, and the other 2 are from Japan and UK. That means he's a pioneer and pillar of this country regarding to wind engineering. He has the Lifetime Achievement Award in 2013 from Indian Society of Wind Engineering during its celebration of 20th year. And again, he got the Distinguished Alumnus Award from IIT Roorkee during 2012. And he got a commemorative volume released in his honor at the National Conference of Wind Engineering, Nagpur, February 2004. And I think today he's going to talk about the cable structures. And regarding cable structures, it's an authority. That's what the following paragraph shows. He got exposure to cable structure during his PhD program, I believe, during November 1961, with experiments on partial model of 4th road suspension bridge. Afterwards, he designed a suspension bridge again, and he worked on a number of cable suspended roofs from 1962 to 64 at Imperial College London to obtain his doctoral degree. He has written a book on cable structures in 1978, and the second edition was published as late as 2013 on. And Professor Prem Krishna, to his credit, has worked on a lot of design structures of membrane structures in India, and his involvement in bridges ranges from studies on cable stayed bridges such as Vidyasagar Setu, complete design of footbridge at Roorkee, which we all used to have and see and witness and benefit. The road bridge at Haridwar being the first cable stayed ones in India, proof checking of number of cable stayed bridges. And apart from this cable stayed activities, he has played a prominent role in INSTAR, promoting the steel construction in the country. And his expert advice has been sought on large steel structures, number of large steel structures, including major railway projects. That's all I have, sir. Thank you very much for accepting our invitation once again. And over to you, sir.
Well, thank you very much. Firstly, my greetings to Dr. Anandwali and colleagues from the SCRC, the present scientists, and maybe some past scientists who may have retired, and all other participants who are at this meeting. I would like to also compliment at this point Dr. Anandwali and the SARC for celebrating the centenary of Professor G.S. Ramaswamy. And he was, as you know, legendary figure in structural engineering, and was also called fondly the Shell Man of India because of his involvement in the development of shell structures for roofing in India. And I thank you for inviting me to this lecture session, which I am sharing with an old friend, Professor A.R. Santakumar. I think I've known him for 40 years or something like that. I also recall that I delivered the first Professor Ramaswamy Memorial Annual Lecture in 2004.
Yes, sir.
I had forgotten the subject, but a little bit more about it later. That was 19 years ago.
Yes, sir.
At this juncture, it is probably natural that I recall the association I had with Professor Ramaswamy when in 1964 I returned from UK after completing my doctoral program as a young man. Professor Ramaswamy was at Roorkee and was already a very well-known figure in the area of structural engineering. Of course, a senior, very much senior person as well to me. And it was natural for me, therefore, to try and interact with him and get advice and so on from him. Also, another reason why I think I wanted particularly to get his mentorship was because of his expertise on shells and my own work on cable roofs, which I had just done at Imperial College. Of course, later he moved to Chennai, and the occasions to meet him became fewer as compared to when he was in Roorkee. But those days meetings and conferences and seminars were held in physical mode, and there were more occasions that way to see each other. And I remember that he was always very kind and to me, and to share with me what I was doing and what was being done at SARC. And of course, I sought his advice as to how to advance my own career. Sometimes at a meeting, in fact, most times at a meeting or a conference, he will be amongst senior structural engineers and I'll be amongst the crowd. But he will make a point to identify me and to wave at me. Or if he was on the dais, then again, he will identify me in the crowd and wave at me. Needless to say that I felt very happy with that and very important because Professor Ramaswamy had waved at me. So those are memories that I have of my association with him as a very kind mentor and a very wise person from whom one could get advice. And I'm sure I've benefited from this. Another common point which I recall, which I want to share with you is the book on shells was mentioned, and that was published by McGraw-Hill in New York. And I think, if I'm not wrong, he was the first India-based structural engineer to get a book published by McGraw-Hill Book Company in New York. And obviously, immediately, he became a very well-known figure internationally. And that, I am sure, gave me the impetus to think of writing a book myself, which I succeeded in writing. on the subject of cable suspended roofs. And this was published by McGraw-Hill again, 1978. Maybe I may be permitted to think that I was the second person after Professor Ramaswamy to write a book of that kind. So those are my thoughts which I want to share with you. I also had delivered the first Professor Ramaswamy Memorial Lecture, 2004, and I had spoken again on cable structures, which I had forgotten. And this time when I was invited, I again chose cable structures. And of course, the reason for this choice then and now was that I have had a number of years of interest in this subject. The second reason is that Professor Ramaswamy was always looking at new vistas. He was always looking at new directions that he created as a pioneering structural engineer in many ways. And I thought to give him a tribute, let's talk about a subject which is somewhat less known. Not so much exposure is there to cable structures. So perhaps at least in that way, one can pay a tribute to his memory. However, I got a little worried when I realized that I had spoken about cable structures in 2004 in almost the similar context, and I'm talking about it again on cable structure. People may think that, he just goes on talking about cable structures every time we ask him. But two things saved me. One was that it was 19 years ago, and maybe, as I had forgotten, maybe my audience will also have not remembered that I talked about cable structures then. The second thing that saved me from getting worried is that in the last 20 years or so, there has been a reasonably good development in cable structures in India, which I can share in my presentation today. Of course, the basics and the fundamentals issues will remain the same as they were at that time. But fortunately for me, and that is what saved my day, is that in the last 20 years or so, there has been a reasonable good development in the area of cable structures in this country. With those few thoughts that I wanted to share with you, I can perhaps now make a presentation to you. But before I start to do that, may I know how much time I have? How much time?
Around 45 minutes, and we are eager to hear you more also.
No, 45 minutes is good. And okay, it's good to have a time frame. Otherwise, to let a white-haired professor loose is not a good thing for the audience. Okay.
So even though this is you're telling like cable structures you have already presented 20 years back, it is always interesting for us to listen from you. The developments, as you mentioned, there is a lot of developments in the recent years on cable structures, and it will be interesting for us to hear. And there are many new scientists who have joined in this institution. They'll be also benefited, sir.
Okay, I'm glad to hear that.
And also, I would like to welcome Dr. Nagesh Iyer and Dr. Pradeep Kumar, Director CBRA, who are joined online.
Oh, okay. That's good to hear that. My greetings to Dr. Iyer and Dr. Pradeep Kumar. May I now begin this presentation? The first slide here shows the types of cable structures, and this is familiar ground. Guide masts is one kind of structure where ropes are used or strands are used, ropeways, roofs, and bridges. Now, in any case, all these structures are not very commonplace. particularly roofs and bridges, are not very commonplace. And to some extent, this is a little bit of a higher end structural engineering, if you like, where you require certain special traits in design, analysis, and construction, and a lot of precision when you take up a cable structure. Next, please. The use of the cable formed with ropes made of high tensile steel, which is 5 to 6 times stronger than mild steel, leads to a system of lighter self-weight. Now, this is, of course, a big advantage, and yet, as I'll mention about it, it also has challenges that gives us. Challenges, because lightweight structures have got to be safeguarded very carefully particularly against wind loading. So that is a challenge that comes to us, but of course, lightweight has many advantages. Now, cables then, of course, combined with reinforced concrete or precessed concrete or structural steel, produce efficient structures. And this is so particularly for medium to long span range structures. Next point, please. Just so that we are talking of cable structures, let us share this cross sections of the cables that you see here, various kinds, strand, parallel wire strand, parallel strands here, if you want a larger size cable, locked coil strand, which is particularly useful when you think of, corrosion resistance, and ropes. Ropes are comparatively more flexible than the strands. And most often, you will find that ropes are used in cable roofs or guide masts and so on. Strands are used more commonly in cable stayed or extra bridges. But that's just a general statement. Next, please. I mentioned that. Next, please. Now, what are the implications of material and form in as far as structures in general are concerned? And particularly cable structures, as we think about in the context of today's presentation. Now, if you look at this slide here, with time, this is the almost about 115 odd kilogram per millimeter square strength, some, let's say, almost 200 years ago, and it has gone on increasing. And the maximum I know of was when the steel was new steel was developed with the Akashi Kakyo cables. That's the highest strength I think we have obtained in high tensile steel wires, and perhaps that is where it is static now. If at all there has been any improvement, there must have been very marginal one. So that's the kind of strength that you have, and as you can see, this is actually about almost 6 to 7 times more than mild steel strengths. Next, that's one aspect of material. Then there are other materials which also offer a possibility of use in cables, but their utilization has been very, very limited. But the point is that you can get material which can be used in cables. For example, this is the carbon reinforced plastic fiber, which is, the properties are shown here. You can see is almost twice the strength. This should be 1800. So still about twice the strength of high tensile steel. The modulus is only marginally lower than steel. The weight is considerably lower than steel, almost a fifth of what you have in steel. So if you really want a very light and strong element or a cable, then this is the kind of material that is available and can be used. It has been used, but in a very limited way so far. Corrosion resistance is excellent for this, and the fatigue characteristics are also good. So there are materials even of higher strength and low weight compared to the highest strength steel that we normally use in cables. Next, please. Of course, then, please, can you go back? Yeah. And of course, as far as concretes are concerned, as we are well aware, much higher strength and concretes are now being are available as compared to the earlier times when we thought of 124 concrete, M15 or M20 or M25 were the strengths that we normally thought of, in let's say 50, 60 years ago. Much stronger concretes are now available and high performance concretes are now available. Now, this brings me to the question of what is the implication of these strengths and weights that we are talking about. The key word here is the strength-weight ratio. And for applications like long span structures, a higher strength-weight ratio or the highest possible strength-weight ratio within the other limitations is a desirable thing to have. The reason for that is that for a long span structure, the self-weight of the structure goes on increasing. Particularly if you think of a suspended cable, the self-weight of the cable itself goes on increasing as the span goes on increasing. And compared to the live load stress that you get in the cable, the dead weight stress is several times more. Therefore, it is implied that we should try to use a material so that the dead weight itself is minimized. That is the implication of this strength-weight ratio. I've just notionally compared values of the strength-weight ratio. These numbers are just normalized numbers, just to see a comparison. And you can see that the high-strength steel here is 240, high-strength structural steel, which is about MPa 800 or so, 80, and mild steel is 20, aluminum alloys 60, and this is concrete, the medium strength concrete, M30. Next, please. Now, also the question of form. How does a structure sustain loading when it's applied to it? Does it take it as a axial force that develops in the member, or it is flexure, or it is combination of direct force or flexure, and so on? That is important, again, when you think of the efficient use of material in a structural form when it is loaded. Now, obviously, ties or struts carry axial loads and are subjected to more or less uniform stress, and thus ensure high utilization of material. However, suspended cables are highly efficient in carrying transverse loads. This is the difference that we need to be careful, to note. Can I see the next slides, please? Next, please. Oh, these are the, that's a strut and that's a tie. And you can see that at the cross section here, it's a uniform stress. And therefore, as I said, more or less, the entire cross section, the material in the cross section or the member is being utilized to a very high degree of efficiency. But that is for axial loads. Now look at the situation as far as transverse loads are concerned. That is on the next slide. Yeah, I have here a beam, a girder, and if you take this cross section here, this is the stress distribution that you see, and obviously only the extreme fibers are being utilized fully. If this stress is equal to the permissible stress, then the extreme fiber is utilized fully, and that utilization goes on reducing as you go from the extreme fibers towards the center or towards the neutral axis, and so on. So the utilization of the material is partial in friction. When we come to an arch, and under the transverse load as applied here, you get a stress distribution of this kind, in which the flexural stress is combined with the axial stress in the arch, and the utilization is fairly good. Also, another aspect of the problem that we need to address here is that in a member which has compressive forces, there is always the possibility of instability, which puts a limitation on to the extent that we can utilize the material. Then we come to the suspended cable here, which is in direct tension. In fact, by way of its proportions of cross-section to the length or the span, it can only take tension, and when loaded, it will displace itself to come into a new set of equilibrium position. Under the dead weight itself, it is suspended here as a catenary, and there is a direct tension that is occurring from one end to the other. That direct tension varies very slightly, maybe 5 to 7% only, between the tension that you get at the center and what you get at the end. So, under its own weight also, it is very highly efficiently utilizing the material. Plus, if you load it, it gets into a new position of equilibrium, but again, only direct tension occurs. A cable, by its proportions, cannot take any compressive forces as such. Whatever compression occurs is local, and that is because of any kind of very limited kind of flexure that may occur at junctions and so on. But that is a very small proportion of the total force or stress pattern on the cross section of the cable structure. And as I said here, it's almost complete utilization of the material that you are using. Now, we just a few minutes back, I mentioned that for longer span applications, it is imperative that through the proper utilization of material of high strength weight ratio and form, we should utilize the material such that with such efficiency that the dead weight of the element is kept to a minimum. Because as I said, it is the ratio of dead weight to live load which becomes higher and higher as the span becomes longer and longer. I may mention this at this point, that for a bridge like the longest span Kashikaki bridge, which was longest span for a long time, not now anymore, the total stress in the suspended cables, 7% was utilized by live load stress, and the rest was utilized by the dead weight stress. If you look at a culvert, which is a 6 meter span maybe, it's the reverse. The live load stress may be 6 times the dead load stress. So this is the change that occurs in the ratio of dead load to live load as we go from small span to a longer span. And I think this is a key point that we need to remember, and that is why the choice of material and form becomes very important. Next, please. Next, please. Can you kindly change the slide?
Yes, sir. Yes, sir.
Yeah.
Yeah.
Okay. Okay. Now this is this.
1 minute, sir. Enough.
Oh, that's you jump
That is
to.
part 2.
I think part 1 is still on.
Okay.
Yeah, this one. I've just shown here the notional, ranges of span that you get. This is so in the next couple of slides also. Concrete slabs normally you have 8 meters as the sort of limit. T-beam and slab about 20 meters, and like that, folded plates, shells, high-power shells. So with the form of the structure, the possibility of going for higher spans goes on increasing. We are not yet thinking of materials here at all. And in fact, what can happen is that if you go for a higher strength weight ratio, maybe the chosen spans can be longer than if you use a material of lower strength weight ratio. Likewise, next please. Yeah. Space grids, lattice domes, generally they'll be using steel. This is a air-inflated membrane roof, which were very common some time back, but I don't see much of that happening now. But in the 60s and 70s, this was a very common manner of designing long-span roofing structures, air-inflated fabric roofs. And here is a typical cable roof, cable net, and so on. And the span ranges, the span ranges here can be seen to be like 30 to 150 meters, while in domes and space grids, this limit may be of the order of about 50, 60 meters, 80 meters maybe. But these here, at least these three, will normally be using steel members. Next, please. This is the same thing, some notional span limits I've shown for girders in bridges. These are the various arrangement for girders. This is the extra doors bridge, which is becoming very, very common now in India. I'll show you a few illustrations of that. And this, you are reaching spans of about 200 meters with these. Trusses you can have up to 200 meters. Arches, you go a little longer, maybe up to 300 meters. Cable stayed bridges, I should put here 1100 meters. I should change this because the 1104 meter span cable stayed bridge already exists. In the last couple of years, it has been constructed. And as far as suspension bridges are concerned, what has been obtained so far or achieved so far is about 2000 meters. But what is being designed for the Messina Stairs Bridge, it has a span of 3,300 meters. I'm not sure when this Messina Stairs Bridge will come about, but the span involved there is 3,300 meters. And in fact, people, there seems to be no limit to the extent that people can think of spans and roofs and bridges and so on. But what is to be noticed is that obviously, if you're going in for these longer spans, and particularly these spans here for cable-supported bridges and suspension bridges, there is no option there to that. Whereas here, primarily, you'll probably get concrete of various strengths. Next, please. Now, as I mentioned, cable structures are not so common in India, but cable roofs in the last couple of decades have come about in this country. I will share a few illustrations with you just to see the kind of roofing systems that have been achieved elsewhere outside the country also and within this country. Next, please. These are the various applications that you get with cable roofs, canopies, exhibition halls, sports facilities, airports, and there are other facilities. Next, please. Next, please. Yeah, this is one. These are some illustrations outside the country. The grandstand roof for a sports stadium. You can see the tall pylons here, which have been stayed back, and from the top, the grandstand roof has been supported. Next, please. That's the Madison Square, New York roof. It's a saucer type of roof, 80-meter in span. This has simply suspended cables forming a supporting system for the roof. And this is again, these are not new ones, these are old. These were achieved many, many years ago. Next, please. That's a roof for a sports stadium again. It has this curved ring beam, and with this, the network has been supported, network of cables, which is a two-dimensional network, and this will carry the cladding. This is about 140 meter in dimension. Next, please. That's the path-breaking structure that was constructed using cables, and this was the dimensions for this roofing are 720 meter by 80 meter. It's a grandstand roof for the Munich Olympic of 1972. 9 80 meter by 80 meter nets supported from edge cables plus 70 meter tall pylons, which were used to stabilize the system. Those were 9 units that were used. The roofing used translucent covering, so that much natural light could get in, through that roofing. So that was a path-breaking cable structure, I would say, which was designed some 50 years ago. Next, please. This is an air-supported membrane roof, which I illustrated with a figure there. This was again almost 50 years ago that this was used. This is the US pavilion at the Osaka Expo in 1970. Next, please. And this is a typical fabric roof with, as you can see, this is a network of cables from which this fabric is attached. And this is typically a fabric roof that was used some years ago. This was also at the Osaka Expo. This is not air inflated. Next, please. Now, the next few illustrations that I'm showing are applications of cables in membrane roofs and buildings in India. And these illustrations are with the courtesy of Mr. Dhananjay Dhake from Construction Catalyzers, Pune. And I would like to mention that it is this firm of Construction Catalyzers which has done pioneering work in developing and constructing a very good number of cable structures in this country in the last couple of decades. Okay, here's a roofing system connecting two buildings. Next, please. Yeah, that's the fabric roof that I'm mentioning. It connects two buildings and it's the entry to these two buildings here. Next, please. Illustration, another view of the same thing. Next, please. The next one is a 75-meter size central atrium for ONGC corporate office building. You can see this. And a thing which I want to point out to you as we are looking at these is that aesthetically, these are very, very attractive structures. But it is also true that it takes a lot of doing in constructing these structures. Requires a lot of very careful planning and accurate work in order to achieve these structures. But they are efficient in utilization of material, they are aesthetically pleasing, but they are challenging in their own way. Also, it is important that we are we are able to estimate wind loading on them in as good, as accurately as possible. Next, please. The swimming pool cover. You can show the next slide, please. Yeah, you can see this. It's all fabric and cable combination. Next, please. This is all construction catalyzers. There's amusement park structure at Rohini, Delhi. Yeah. Fabric and cables again. Next, please. Then you see the roof over the rapid metro station in Gurugram. Next, please. That's the roof. That's again fabric roof. The fabric is connected to steel arches. Like that. You can see the train coming through. Next, please. And then there's the Atrium Mall in Mumbai. You have a very large glass panel which has been supported on a system of cables. You can see two-dimensional network of cables here. And this is what is supporting a large glass panel here, large glass facade for this Atrium Mall. So another kind of use of cables that you see here is not roofing, but it's a facade. Those were few illustrations then of cables being used in India, and I'm sure the total count may be, I won't venture a guess, but must be at least 25, 30 structures of that kind in the country now. And these are mostly done in the last couple of decades, since the 2004 lecture I gave. So that's the implication. Subsequent to this now, I think the part 2 will come. Yeah. Now, can I have the previous slide, please? Yeah. So cable stayed and extra type bridges coming into use increasingly in India. Cable stayed bridges started appearing almost, I would say, about 40 years ago. And the extra bridges are a later development, but the extra bridges seem to have caught on very fast. And in this respect, I would say, perhaps, as far as extra bridges are concerned, our engineering is possibly at par with anywhere else in the world. Next, please. The Indian Road Congress is about to publish guidelines shortly on the design of cable-stayed bridges and extra bridges. I think within the next couple of months, we might see these documents they will see the light of the day. And I can say that because I've been associated, I will say that these are guidelines which will, of course, be very good for our own engineering, but even people outside this country may be able to appreciate how well they have been prepared. Now, the present tally of cable-stayed bridges and extra-dose bridges in the country, cable-stayed bridges about 20 completed, about 10 ongoing. The span ranges very interestingly, even 20-meter ones are there. But these have been done for the sake of just having a little cable-stayed bridge somewhere, somewhere in the city, just as a piece of attraction. But by and large, cable-stayed bridges will be more acceptable in longer ranges of span. But at the other end, of course, we have a 500-meter span bridge also under construction. Then you look at the extra-dose bridges, about 15 completed, about 20 ongoing, and the span ranges for these bridges approximately 52. The maximum is 230 meters currently. And so this is the range of spans for extra-dose bridges that are in India, either constructed or completed. Next, please. A few illustrations. Next, please. This is one illustration of a bridge outside the country. The only one, I think. That's the Tatara Bridge. Just hold on a minute, please. Can we go back to Tatara Bridge, please? Yeah. Tatara Bridge has a main span of 890 meters. And this was constructed about 20 years ago. And it held the record for the maximum cable-stayed bridge for many, many, many years. But of course now, in the last 4 or 5 years, this has been bettered. And as I mentioned a little while ago, the longest span cable-stayed bridge now is 1104 meter span in Russia. But for many years, this was one bridge that held the record. Alongside this, there was the Akashikake Bridge, the suspension bridge, which had a span of 1990 meters, almost 2 kilometers. And that also held the record for almost 20 years. Now, according to me, these two bridges in Japan, they pushed the frontiers of bridge engineering technology in many ways. There was a lot of innovative work done, a lot of developmental work done to get these bridges into position. And that pushed the technology for bridging substantially. I think these two bridges, I always hold them in, as bridges of pride. Next, please. This is a short span bridge, cable-stayed bridge at Hardwar, 130 meter long. So each side of the central pylon is 65 meters each. But the distinction here, I think the credit here is that this was the first bridge, road bridge, which was cable-stayed, and that in India. And before this, there was a small bridge over the canal at Roorkee, 73 meters. That was in 1982. And that was also, I believe, probably the first pedestrian cable-stayed bridge. And this was 1988, this one. Next, please. That's, of course, the formidable Vidyasagar Setu, completed in 1992. And the main span is 457 meters. The side spans are approximately 225 meters. And this was the second bridge over the Hooghly after the Howrah bridge. And at that time, It was one of the, one of the longest cable stayed bridges, not the longest. So that was again a very great achievement of Indian bridge engineers at the time. Next, please. Centenary Bridge came later. It's about 260 odd meters here, nearly 300 meter span, and side spans about 125 odd. So that's Centenary Bridge, that's the cable stayed bridge again. But there are other examples of cable stayed bridges now in the country, as I, of course, that table showed the number. Only I have picked up a few photographs. Next, please. The illustrations that I'm going to show next are for extra dose bridges. These have come from Mr. Alok Bhaumik, whose firm has been doing a lot of work on extra dose bridges. They're one of the leading designers of extra dose bridges in the country. So here are a few illustrations. This is a second Vivekanand bridge, the Nivedita Setu, with a 110 meter longest span here, and combination of smaller spans. Completed 2007. Then you have the Mulchand Bridge, and this is in Delhi, 2010, I think, completed. Next one, please. This is the extra dose bridge over river Etania do Enya in Noida. Okay, the span is 168 meters. Next, please. This is rather important. The Ara Chapra Bridge, which is called also the Veer Kumar Singh Bridge, is the world's longest extra dose bridge, and this is over the river Ganga. And the span arrangement, it has multiple spans of 120 meters each. And it had the distinction of being the longest extra dose bridge in the world. Next, please. I think this covers the illustrations. Now, there are a few special issues related to cable structures. I think another 5-7 minutes I should be through. Next, please. Of course, related to cables. Now, there are a few issues that need to be addressed when you think of cables. One of them is the resistance to corrosion, that is, protection of the cable with suitable coatings. Now, zinc coating has been known to be very common, and there are other possible ways of coating the cable also, as are listed here. And polyester coating is one possibility. Then also some people have placed a cable within polyethylene tubes and then grouted the space between the tube and the cable steel to protect this cable steel. That also has been used, but currently not many people would think about using that because there are better ways of doing it. Then also people thought of injection of hot dry air through the space between the outer covering of the cable and the cable steel, so that the moisture could be kept out. There's another way it was actually also employed. So there are various ways in which you try to keep your cables from getting corroded and therefore deteriorating. Next, please. Yeah, obviously you want as much stiffness in the cable as possible, because the stiffer the cable, the lesser are going to be your deformations. And in this respect, as I mentioned earlier too, parallel wire strands will show a greater modulus, axial modulus, than would be twisted strands or ropes. Ropes, for example, may be 80% as compared to parallel wire strands. So it is mostly parallel wire strands that you will find employed in cable stayed bridges and extra dose bridges. Also, fatigue strength should be adequate, and for that the anchor arrangements are an important issue to address. Next, please. As far as analysis is concerned, cable roofs are assemblies of flexible cable systems with comparatively rigid supporting elements. Cable bridges consist of cables interacting with rigid towers and decks. In both situations, there is a large degree of indeterminacy, and also non-linearity is an inherent part of their response to loading. Now, cable-stayed bridges would be found to be stiffer and the non-linearity will be limited. Cable roofs perhaps may show you more non-linearity. Now, as far as this large degree of indeterminacy is concerned, it perhaps used to be a matter of concern 70 years ago, before the digital computers with high-speed possibilities came in. And in fact, if sometime we can discuss this, earlier cable-stayed bridges were specifically designed with few number of cables so that the indeterminacy will be limited, because making calculations for highly indeterminate structures was difficult without computers. So the design was affected by that, but no more. That is not an issue anymore. Similarly, non-linearity is not an issue anymore. Of course, we are in a very comfortable situation currently, where the problems of analysis, howsoever highly indeterminate the structure is, or howsoever the non-linearities are involved, it doesn't really cause much concern to us, because there are ready-made software packages that can handle all these issues very, very comfortably. So today we are very comfortable. But when I was doing my PhD, I had to solve six simultaneous equations, and that took me a whole day using a mechanical calculator. That was 1963. So today I feel that we are much more comfortable. Next, please. These are various kinds of nonlinearities. Geometric nonlinearity, when you get large displacements. Then you have cable sag effect, that also causes nonlinearity behavior between load and deformation. Then you have axial force versus flexure interaction. This will be so in pylons for a cable stayed bridge. And if the material is nonlinear, the stress strain curve is nonlinear, then of course you also have material nonlinearity, which is not so much an issue really, not with cables, not with steel members. Maybe fabric may show some nonlinearity. Next, please. Yes, that's an issue which I'll only touch upon, but it is a whole subject by itself. Because as I had mentioned right in the beginning, you get these lightweight structures. And of course, it's a benefit to have these lightweight structures in many ways. You get lighter foundations and so on and so forth. And lightweight also means that you are using less material. So all that is there, all the advantage is there. But then if you think of lightweight structures, they become prone to different forms of effects due to wind, both static, equivalent static as well as dynamic. And this is a problem one would face both in roof as well as bridges. Of course, obviously wind causes non-uniform loads, that's okay. Tension roofs are often lightweight, and as such, wind forces can cause large displacements because of wind. The fluctuating nature of wind load causes vibrations in the roof structure and its various elements. Since cable roofs have non-conventional geometric shapes, wind pressures for these are commonly not covered in design loading codes or existing literature on the subject. So this is something that we need to create a database for various forms of roofing systems that we have. Next, please. Compared to what normally happens in a, for example, in a beam, the whole span loaded will give you the worst effects as far as stresses and displacements both are concerned. Not for a cable. Of course, the maximum stress will come with full loading. So that is the difference between a cable and a conventional girder. Next, please. Yes, and as I mentioned, non-uniform loading. Here is an example. You can see that in a roof structure, the variation of pressure coefficients is huge. You see here from minus 0.08 to minus 0.45, which is the highest. Minus, and yes, plus 0.5. So there's a lot of variation on the surface of the roof, which we must cater to after we have determined this. Any kind of crude approximations can be, a cause of difficulty. Next, please. As for bridges, box girder bridges which are aerodynamically shaped experience less less wind forces compared to truss systems. Next, please. Often multiple box systems are used for large span bridges in cable stayed suspension bridges or cable stayed bridges. And this is an example for the Messina straight suspension bridge deck. This is an old picture. I don't know what is the latest situation, but the point that I'm trying to make is that very often you get multiple box systems which are combined to form the box girder for a long span bridge. This is aerodynamically shaped, so it attracts less wind. Plus, because it's a box system, it is torsionally stiff. If you don't have torsionally stiff systems, then you can get problems of aerodynamic stability of the kind that happened in the Tacoma Narrows Bridge. Next, please. You can also have cable vibrations occurring, which you have to safeguard against in various ways. Next, please. You can use auxiliary cables, or next slide will show dampers. Yeah, you can use dampers to control vibration in the cable stays. Next, please. Construction sequence is extremely important. Appropriately chosen erection procedure is of vital importance for safeguarding the supporting structure from getting overstressed. Now, this is something, because we are not so exposed to the construction of cable structures in this country, this is a fact which is often lost sight of. And this can be a cause of a lot of problems in practice when we actually start constructing these structures. So this is something which I always say, if you are looking at the design of a cable structures, please ensure that you simultaneously look at the process of erection that has been assumed by the designer. That is a must, that must come along with the design of the bridge, whether it's a roof or a bridge, in fact, both cases. Next, please. In conclusion, I am only saying that although we haven't done too many cable structures in this country, the capability exists, and I think the idea is to use them, gain more experience. But I will add to this, this point here, that I believe that this cable roofing really utilize that potential to the extent that we can. And one of the reasons why this is not so, and I'm saying this with Dr. Anandwali sitting here and Dr. Pradeep Kumar both heading research institutions, CBRI and SCRC, that there is a need to do much greater work in terms of research on these structures within the country. I think that will strengthen our hands to utilize the potential of these structures much better than what we have done so far. Next one, please, is the last slide. The last slide is a vision I want to share with you, and this is to do with aesthetics of structures. The great spans of tomorrow, spans that will win hearts, will have simplicity of form, beauty of line, grace of proportion, harmony of color, and radiance of illumination. Beauty will be secured without sacrificing utility or economy. The modern designer must bring to his understanding of structural design and functional values a strong feeling for beauty of line, form, and proportion. If he does not give his heart and his mind to making the works beautiful, he is betraying a moral obligation and a civic trust. So that's our mandate. Thank you very much, friends. I'm very happy to have been able to share my thoughts with you, and I thank you very much for your patience.
Professor, I think you have highlighted right from the span, materials, forms, and how strength to weight ratio by using cable structures helps us to proper utilization of the materials, and also illustrations to make the presentation very lively. And in the end, you were also highlighting the issues, various issues like corrosion of cables and analysis, what are all the intricacies we have to see, and also wind loads and aerodynamics, which we have to look into for non-uniform loading, large deformation, vibration. And this also you have in the end laid down a vision for us to move forward in this area. And also the construction sequence, which we normally fail to address, that also highlighted upon, sir. And thank you, Professor, for your elaborate lecture in this on cable structures. And you have taken our attention, not partially or good, but almost completely. Thank you, Professor.
Thanks very much.
Now I request Dr. G.S. Parani, Chief Scientist and Editor TRS, to introduce Professor Santakumar.
Respected dignitaries, my dear colleagues, invitees, ladies and gentlemen, very good afternoon to all of you. It's my pleasure and privilege to introduce Professor G.S. Santakumar to this august audience. Professor G.S. Santakumar is from our neighboring institute, Anna University, and is very familiar to all of us. And many of our scientists may have been students at some time or the other. So he's a very popular figure in our campus, but still, as the occasion demands, I will make it very brief. Professor Santakumar is a former dean and chairman of Faculty of Civil Engineering, Anna University, and a former emeritus professor in Indian Institute of Technology, Madras. He was advisor, Shelter Reconstruction and Rehabilitation, United Nations Team for Recovery Support, UNDP, India. Professor Santakumar received his MSc Engineering degree from the Madras University and obtained his PhD from the University of Canterbury, New Zealand, as a Commonwealth scholar. He has contributed a number of research papers in national and international journals and delivered lectures in New Zealand, Australia, USA, and Singapore. He has coordinated the International Conference on Disaster Mitigation and Management during 1977 and a number of workshops in the field of concrete construction. Professor Santakumar has set up the Center for Disaster Mitigation and Management with assistance from UNDRO and Building Technology Center with assistance from ERCO at Anna University, Chennai. He was responsible to introduce MS by Research and ME in Construction Engineering and Management at Anna University for the first time. Besides teaching, he guides PhD students, provides consultancy to many organizations in concrete construction engineering problems. He has designed number of infrastructure projects such as bridges, shelters, towers, dams, and plants for major public sector corporations, railways, and government of Tamil Nadu. Professor Santakumar has received many awards. I will mention some of them. The ACC Nagadi Award for the best book published on transmissional networks by McGraw-Hill, Singapore, International Edition in 1993. And this was awarded by Association of Consultation Engineers, India. He has also published a very popular book on the concrete technology published by Oxford Press, which also received the ACC award. Recently, he was acknowledged as an outstanding academic person and was awarded the prestigious Vishwakarma Award of the Construction Industry Development Council, Government of India. With this brief introduction, I will now call upon Professor Santakumar to deliver his invited lecture. Thank you very much for this opportunity.
Thank you very much for the nice introduction. It is my pleasure and privilege to talk in this forum got up to commemorate Professor G.S. And before I go to my lecture, I would like to recollect my association with Professor G.S. In fact, my association with Professor G.S. dates back to 1970 when I met him in Chennai. And at that time, he had suggested that I work on shear walls and tall buildings. Even today, I remember his words encouraging me to take up research in shear walls. I have continued to work on shear walls, and I deem it a privilege to speak here on in this forum, which reminds me of my association with Professor G.S. A few important projects we did together. One of the projects that we did together was development of a nodal system for space structures, which I used newly developed node, very similar to the Mero node already patented. And this new node was utilized in almost all the IOCL bottling plants. And that gave me a lot of satisfaction. That was the first project I did along with Professor G.S. The next project in which I worked with him was the tennis stadium in Madras, which again had a space structure for its roof. And the contribution of, as I may call it, my mentor can be expressed in no small words. So when I was approached to speak in this occasion, I decided that I will speak on earthquake as well as modern methods that are used in structures to withstand or to overcome the lateral loads caused by earthquake. May I go to the slides, please?
Yes, sir.
Are you able to see these slides?
Yes, sir. We are able to see.
Okay. Oh.
Sir, it's not yet opened. It's not yet opened.
Oh, you have not shared it.
Oh.
Board.
There.
Shall I share it?
Now it's coming, sir.
Oh.
Is it okay?
Yes, sir.
Whether it's visible to everyone, like
Yeah,
I think it is visible, sir.
Yes, yes.
The topic which I have chosen is modern concepts of earthquake resistance in structures, and this I thought I would present with respect to introduction of shear walls in multi-story buildings to limit lateral load deflections, as well as to introduce a favorable behavior when tall buildings are subjected to seismic forces. The presentation I have divided in these parts. First, a brief introduction, then composite coupled shear wall systems that are currently used in tall buildings, then shear truss frame interaction systems that are used in tall buildings, then outrigger shear truss frame systems, then ductility of strength of walls, elastic plastic behavior of the coupled system, strengthened ductility of link beams, and a comparative performance in the end. One of the problems that we are facing in earthquake resistant design is that the design that we make has to withstand lateral load due to earthquake as well as vertical load due to gravity. The problem that arises, which is not faced in other loading conditions, but is faced in the earthquake situation, is that we don't know the correct load that will come on the structure. Therefore, we may not be able to design for a particular load only, but we will have to design for a fail-safe system which will incorporate on one side a load which will withstand gravity load at all times and provide ductility such that the energy absorption capacity that is developed by the earthquake is adequately withstood by the system we propose. Therefore, the system that we propose in tall buildings becomes of paramount importance, not only from the point of view of withstanding the gravity loads, but also in dissipating the energy due to earthquake. Therefore, unlike other design parameters, we have here twin requirement of a particular load carrying capacity and a lateral load capacity. In this, one disadvantage that exists that is not felt in other loading condition is that when the earthquake load occurs, the resisting mechanism is damaged, and this damaged resisting mechanism has to resist the vertical gravity load for the purpose of safety. Therefore, there is a disadvantage in that the load resisting mechanism is damaged by the lateral load, but the same has to be withstand the vertical loading. So what is the development that has taken place in codal provisions today? Deal with a system in which we have a particular load capacity and we have a required ductility capacity so that the energy absorption is adequate with respect to earthquake performance. Therefore, let us look at the systems that we are using for such a mechanism. One of the developments that is taking place is using a composite coupled shear wall system. If we take a shear wall is pierced by the number of openings. Because the shear wall is pierced by the number of openings, we have two walls connected by a series of beams. Now, what is shown in this figure is the equivalent column and equivalent.
Professor, figure is not coming. Professor, figure is not coming. It is now. Okay, now it's come. Thank you.
Are you able to get the figure?
Now it's come, sir.
Okay.
Yes. Now it's available.
Okay. We have a vertical pier connected by a series of coupling beams. Normally, we have piers in concrete and coupling beams with reinforced concrete. Now you can see that when the beam deforms, there are inside the shear wall, there is non-deformable portion of the beam. Because there is a non-deformable portion of the beam inside the shear wall, the lateral load tries to bend the shear wall as I have indicated here. Non-deformable portion of the wall and deformable portion of the beam. This beam is known as the coupling beam. In an actually earthquake situation, the two walls connected by a series of beams develops yielding of steel at the two extreme ends, which can be clearly seen in this slide. Now, what the difference between a frame and a shear wall is that in the case of the shear wall, when the beams get damaged, the walls are still intact. And because the walls are still intact, the gravity load system is not disturbed, and the gravity load system is able to take care of the safety of the structure. The damaged portion is confined to the coupling beams, and therefore the coupling beams become very important in the behavior of multi-story buildings with shear walls with openings. Now here again, I have reproduced the same deformation capacity of the coupling beam. The core walls are essentially shear walls that can be analyzed as planar elements in each principal direction or as a three-dimensional elements using computer program. The ductility of the system can be enhanced by providing diagonally reinforced coupling beams. These diagonally reinforced coupling beams pose constructional difficulties. composite coupling beams in the form of link elements in steel offer very good alternative and results in superior performance. That is, the composite coupling beam involve reinforced concrete walls, but the beams are made with steel embedded in shear wall on either side. Coupled shear wall, therefore, is shown to be with link steel beams. If I take two shear walls with a breadth B with a gap in between them, the moment of inertia of each wall is 2 into TB cube by 12, which is approximately 1/6 TB cube. If I put these two walls together, the width of the wall becomes 2B. So the moment of inertia becomes 4/6 TB cube. So by putting the two walls together and stitching them together, I am able to get 4 times stiffness as I would get with the individual walls. These individual walls actually have a gap, and this gap is provided by is filled by the coupling beam. So if the coupling beams have infinite stiffness and keep these two walls together, I will have 4/6 TB cube. If the coupling beam has 0 stiffness, I will have 1/6 TB cube. And therefore, the actual stiffness of the beam, if I substitute, I come to the conclusion that the stiffness will be between 1/6 and 4/6, depending upon the efficiency of coupling that I am making between the two shear walls. Now, the type of forces that get generated in the shear wall I have shown here, it is the shear at the two ends of the beam. Rigid frame systems are not efficient for buildings over 30 stories in height because the shear racking component of deflection caused by the bending of columns and girders cause the building to sway excessively. Not only that, such excessive swaying buildings invite problems during earthquake, and the earthquake load has to be withstood by the same system that resists gravity load resisting mechanism. On the other hand,
Professor, excuse me.
Yes.
Excuse me. Are you moving the slides? I have a doubt whether the slides are moving.
Yes, sir. The slides are not moving. We are in the third slide.
Okay.
Maybe you can just say, next you can just say, then we'll, oh yeah.
Now, shall I?
Now it's slide number 5 is being shown, sir. Slide number 5.
Can somebody assist me in moving the slide from your end?
Yes, sir. We will do it, sir. Now
Okay.
you are the fifth slide, sir.
You can stop sharing, Professor, then they will start doing.
Yeah.
We will share it from our side.
Yeah.
Professor ARS, நீங்க stop share பண்ணிடுங்க.
இங்கே பண்ணலாம் சார். No, he cannot done now. Right now he's not thinking. No, he is right. I see it.
Right now we are in the fifth slide, sir.
Right now I am in slide number 4.
That, no.
From 4,
Okay.
will you be able to share the slide?
Yes, sir. Yes,
No,
sir.
it's,
I'm able to do
it's
it.
4.
You just tell just please explain. I'll do it, sir.
Okay. The core walls are essentially shear walls that can be analyzed as planar elements in each principal direction or as 3-dimensional elements using computer program. The ductility of the system can be enhanced by providing diagonally reinforced coupling beam. They pose constructional difficulties Because they pose constructional difficulties, composite coupling beams in the form of link elements in steel offer very good alternative and results in superior performance. Now let us go to slide number 5. Can we go to slide 5?
Yes, sir. It's in the slide 5, sir. We are in the 5th slide.
Yeah. Okay. Now in this you can see that moment of inertia of the two shear walls when they are separated by a gap is 1/6 TB cube. If they are put together, it is 4/6 TB cube. If I introduce the coupling beam, it is between 1/6 to 4/6, and whether it is near 1/6 or 4/6 depends upon the coupling efficiency. In order to increase the coupling efficiency, we can go to the composite coupling beams. Next slide. Slide number 6, please. Yeah. Rigid frame systems are not efficient for buildings over 30 stories in height because the shear racking component of deflection caused by the bending of columns and girders causes the building to sway excessively. On the other hand, vertical steel shear trusses or composite concrete shear walls alone may provide lateral resistance for buildings up to 10 to 35 stories, depending upon the height to width ratio of the system. The approximately shear type deflection profile of moment resisting frame when combined with parabolic cantilever sway mode of shear truss or shear walls results in a common shape of structure with two systems are forced to deflect together. Slide number 7, please. Now this shows how the composite shear wall system bends and is advantageous. The frame deflects in shear mode, the wall deflects in flexure mode. When these two are put together, interactive forces develop, and note that these interactive forces help the behavior of both the shear wall as well as the behavior of the frame. This becomes the composite concrete shear wall system. Slide number 8, please. If we look at shear wall core supported outrigger system, during the last few decades, several buildings have been built utilizing belt truss and outrigger system for the lateral load transfer throughout the world. The system is very effective when used in conjunction with composite structures, especially in tall buildings. The core may be centrally located with the outriggers extending on both sides, or in some cases, it may be located on one side of the building with outrigger extending to the building columns on the other side. Slide number 9, please. This shows a typical outrigger system, and you can see that you have super beam at the top and you have the shear core. The shear core itself is made up of coupled shear wall, and damping is provided here. The outriggers take on resist gravity loads. So at no point of time the gravity load is compromised. All the lateral load effects, major lateral load effects is picked up by the outrigger system. Slide 10, please. Whenever it is frame shear wall, shear truss system or outrigger system, or the buttressed core system used in Burj Khalifa in Dubai. This type of bending moment develops. Without the outrigger, for the lateral load, this will be the bending moment diagram. The outer dotted line will be the bending moment diagram. Because of the outriggers, you can see how the moments get reduced right along the height of the building. And not only that, the earthquake load is taken by the outriggers, and even if the outrigger gets damaged, the load carrying capacity of the shear core will support all the gravity loads that are present in the structure. Next slide, please. Ductility of and the strength of composite shear wall is much better. Since the shear wall carries large gravity loads also, it is necessary to provide confinement reinforcement to improve ductility to adequate levels. Closely spaced transverse ties are provided around the vertical flexural steel, which may suffer softening during cyclic loading due to Bioshinger effect and the opening of cracks. The spacing confining composite boundary element in such cases could be even less than that recommended by the code. Figure shows the improvement in ductility of composite elements are placed. This shows a typical analysis result wherein you can see that when I am placing the reinforcement in the boundary element, both the ductility and the strength of the shear wall increases, and therefore instead of placing reinforcement only in the boundary element, in the boundary element, boundary elements are made as composite elements. Concentration of steel near the edges of the shear wall increases both the stiffness as well as the ductility capacity of the composite shear wall. Slide 13, please. Now, how does this bend, when the coupled shear wall bend is shown in this? The walls are connected by link beams. These beams are known as the link beams, which are short and deep. A coupled shear wall structure and the deformations due to lateral loading is shown in this figure. You can see that when the coupled shear wall is subjected to lateral load, you have three areas of distress. One is the coupling beam, which is marked as 1. The second one is the tension wall, marked as 2. And the third one is compression wall, marked as 3. As long as the coupling beam is designed such that it picks up all the lateral load, 2 and 3 will behave in an elastic manner, carrying all the lateral loads, whereas the coupling beams will provide the required ductility. Now, the rotation capacity of the coupling beam is shown by a picture here. So in this picture, we can see that there is an enhancement in the rotation in the coupling beam when the wall rotates by theta p. The coupling beam rotates by theta p into L wall by L. This L by L becomes a multiplication factor. The distortions in a laterally loaded coupled shear wall is shown in this figure. 14th slide, please. If I take the overturning moment as m0, that overturning moment m0 of the building can be divided into 3 components, m1, m2, and LT. m1 and m2 are the moment capacities at the base of the walls, and LT is the tension compression couple that invariably develops due to lateral loading. The axial force induced in the wall result from the accumulation of shear in the beams. These axial forces, T, is due to accumulation of shear from the beams. If the shear transfer is efficient, this LT component will be large. This is desirable since large internal lever arm L will ensure that the moment capacity is maintained. Therefore, if LT becomes large, M1 and M2 become small, and with a large LT, the ductility is being provided by the coupling beams and not by the walls. If I make LT small, M1 and M2 will become large, and when M1 and M2 becomes large, the gravity load carrying system gets affected in the shear wall building system. Slide 15, please. Now, how to make, therefore, the question that is being addressed is how to make LT component high. To make the LT component high, the coupling beam should become very efficient. To make the coupling beam efficient, there are 4 different methods suggested in this slide. Method 1, conventional reinforcement for flexure and shear in the coupling beam. Method 2, diagonal reinforcement of the coupling beam. Method 3, providing a steel beam for taking the shear and making it efficient. Method 4 is a composite system with yielding type of stiffeners in the steel beam. It has been found that the composite system has the maximum energy absorption capacity and provides with maximum efficiency so that the LT component becomes high and M1 and M2 becomes low, so that the gravity load resisting mechanism is not disturbed. Slide 16, please. Now, this slide shows how the efficiency changes the moment pattern at the bottom of a shear wall, of a coupled shear wall. This is a lift well with 2 channels provided with coupling beams, and the coupling beam efficiency is varied by varying the type of coupling beam and also the depth of coupling beam. When the depth of coupling beam is low, we have LT component small, which is around 25%. When the depth of coupling beam is about 1 meter, the LT component becomes nearly 65 to 70%, and M1 and M2 put together is only 25 to 30%, making it a very efficient shear wall, because when the efficiency of the shear wall goes high, the wall bases are protected and gravity load transfer mechanism is preserved. On the other hand, if I have a low efficiency coupling, the capacity of the walls will have to be utilized for lateral load, and if that is utilized, the gravity load resisting mechanism is disturbed and the multi-story building will have no other option but to collapse. Slide 17, please. Now, how is the ductility varying in these coupling beams along the height is indicated here. This is the load displacement curve, and up to around 80% of the coupling beams are plastifying. The walls are still elastic. Laminar shear force distribution and ductility demand is shown in this, and the ductility demand shows that up to about 85 to 90% of the coupling beam getting damaged. The walls are still intact, and therefore elastic plastic behavior of the multi-story building will be maintained without any difficulty. Slide 18, please. Now, instead of viewing it as a coupling beam, if we view that as a link beam, which is a concept, the link beam dissipates energy by controlled yielding in shear or moment. This controlled yielding in shear and moment can be achieved by suitably designing the link beam. Hence, it combines the advantage of both steel moment frame and shear wall. The critical beam segment called link of designed length E links the system. The system that it links is on one side tension wall, on the other side compression wall. Links the system, these link beams act as structural fuses. It dissipates seismic induced energy in a stable manner. Links are properly detailed to have designed adequate strength and stable energy dissipation. All other structural components of the composite shear wall system, walls and connections, are designed using capacity design concept to remain elastic, while the link beams yield and dissipate energy in a very ductile manner during a major seismic event. In this such a situation, the link beam alone will yield, absorb energy. The walls will be elastic. Because the walls are elastic, no damage will happen to the walls. Slide 19, please. On yielding of the link beam, plastic mechanism is shown in, this is the plastic mechanism. Here, the walls don't yield, the link beams are all yielding. This shows the rotation capacity that is available in the link beam, which can be computed analytically. Slide 20, please. A short link is used so that the link will primarily yield in shear. Assuming that the link behaves in an elastic, perfectly plastic bilinear manner, using simple plastic theory, the ultimate load can be predicted for the link beam as Pu is equal to Vp into L divided by H. Figure shows the free body of the link. Flexural hinges form at the two ends of the link beam. The flexural hinges have capacity MA and MB, reach plastic moment MP. A shear hinge is said to have formed when the shear reaches VP. Plastic and shear capacities are respectively computed as, this is flexural capacity, this is the shear capacity, because this will be a composite beam. Next slide, please, 22. This is the link beam, MA and MB. VE is MB, VE is V, this is shear, V into E is equal to MA plus MB, free body forces of the link element. Next slide, please. 23. 1/4 full-size model test results are available. If the link is detailed properly, you get a very favorable hysteresis loop, whereas if the link is not detailed properly, you get shear pinching and energy dissipation is not good. So designing the link element becomes an important issue for a very good behavior. And if we get this very good behavior, the two systems, lateral load system and vertical load system, can be separated, and vertical load system can be preserved when the lateral load system will utilize the link beam for making the link beam energy dissipation a reality. 24th slide, please. Now, in the link beam, you have the concrete slab also. Research conducted on composite links showed that the composite action can be increased, can increase the shear capacity during the first few cycles. However, composite action deteriorates due to damages in both ends of the floor slab. For design purpose, shear strength of the slab can be ignored, but the overall over strength should be considered while designing other members to be elastic. We will have to design the two walls to be elastic. 25th slide, please. Link detailing. Full depth web stiffness must be placed symmetrically on both sides of the link web and at the ends. The end stiffness should have combined width not less than BF minus TW and the thickness not less than 0.7 TW or 10 mm, whichever is larger. What to idealize is we should see that the detailing of the composite link beam should be such that premature shear failure should not occur, and energy dissipative tension field action develops. The link section should satisfy the plastic requirements as specified for special moment frames. The link needs to be stiffened against web buckling as well as flange buckling. 26th slide, please. Beam outside the link. The link end moment has to be borne by the beam outside the link. The link end moment should be calculated with a factor 1 so that the outside the link beam is not plastifying. Only the link portion should plastify. 27th slide, please. Capacity design of other structural components. Links are designed as fuses and are sized to resist design seismic force. All other elements of the system are then designed for forces generated by the actual capacity of the link. Link has to plastify and other elements are designed to be elastic. The capacity design concept thus requires computation of the link strength is not only based on expected yield strength of steel, but also includes the consideration of strain hardening and overstrength. The strain hardening effect and overstrength has to be considered, and the capacity design principle will have to be used for the design of the walls. 28th slide, please. This shows a typical multi-story building in which the link beam has been provided with composite deck slab. The shear studs can be seen in the composite deck slab. 29th slide, please. Now we have seen three systems. One, conventional coupling beam. Second, diagonally reinforced coupling beam. The third one is link beam coupling. What I have provided on the vertical axis is the shear capacity. What I have provided on the horizontal axis is the energy dissipation capacity of the three different systems. System 1, conventional coupling. You can see that the capacity is less, the energy absorption capacity is also less. That has been improved by diagonally reinforced coupling beam. That has been improved by link beam coupling. And therefore, by using the link beam coupling, we should be able to get much better performance in earthquake resisting systems. Thank you very much. These are the references from where I have taken. Thank you very much for inviting me to participate in this very important program.
Thank you, Professor. You have taken us through the journey of coupled shear wall system, and right from the differences between framing system and to shear wall system. Also, you have highlighted the construction difficulties and how link beam acts as fuses and how these systems are very efficient. Also, I have highlighted the advantage of outrigger system and importance of detailing, how different parameters affect the composite system, wall system through simple equations. Also, I have given the principles of design, detailing, and some guidelines on these composite shear wall system. In essence, Professor, you have shown us a combination of rigid plus flexible is very effective, which is true for our life also. Thank you, Professor.
Thank you. Thank you very much.
I now request Dr. K. Satish Kumar, Chief Scientist and Head BKMD, to propose vote of thanks.
Professor Prem Krishna, sir, do you want to say anything? I hope you want.
He was acting from the way that.
You have to unmute, sir.
Yeah, yes, I unmuted. Well, one thing I want to say is that to very appreciate Professor Santakumar's lecture. It was a really solid, surreal exposition of the subject, which I enjoyed very much. And another aspect, I think, to be sharing a platform with him, and he's talking about earthquake engineering, which was something in which my father was deeply involved and interested. It was very nice, and it's a great pleasure to be here. And say that I'm sure Kumar will share that thought. It's a great privilege for us to be part of this lecture session where we are commemorating the great engineer Ramaswamy. Thank you very much indeed for inviting.
Thank you.
Dr. K. Satish.
Good evening to everyone. It's my honor and privilege to propose a vote of thanks and to acknowledge the contributions of those who worked hard for the successful organization of the first lecture series as part of birth centenary celebrations of Professor G.S. Ramaswamy, fondly called Professor G.S.R., the founder director of this great institute, CSIR-SCRC. On behalf of director and my own colleague staff of CSIR-SCRC, I give a really heartfelt thanks to our chief guest, Professor Prem Krishna, distinguished structural engineer and former Professor Emeritus, IIT Roorkee, and Professor A.R. Shantakumar, former Dean, and Professor Structural Engineering, Anna University, and Professor Emeritus, IIT Madras, who have spent their most valuable time in gracing the occasion, gracing the celebrations, and to deliver the motivational lectures in spite of their busy schedule. Thank you very much, sir. Today, we all feel proud and honored by your presence, and your lectures have enlightened our young minds. I understand that many of close associates of Professor GSR, well-wishers of CSIR-SCRC from neighboring institutions including Anna University, IIT and BIT, members of various structural engineering associations including ACCE, ISWE, ISET, IEI, former senior scientists and colleague staff of CSIR-SCRC, and scientists from sister CSIR laboratories including CSIR, CBRI, have participated in this event through virtual mode. To mention a few, Professor M. Shekhar, former professor, Anna University, and Nageshwar Iyer, former director, CSIR-SCRC, Dr. Pradeep Kumar, director, CBRI. My heartfelt thanks to every one of them for their virtual presence here today to make the event a grand success. My sincere thanks to goes to our director, Dr. N. Anandavalli, for her initiatives and continuous support in successfully organizing today's event. With deep sense of appreciation, I thank Dr. B.H. Bharat Kumar, Advisor Management, for the valuable support in planning and coordinating the entire event. We have been fortunate to have a dedicated staff from ICT, VKMD, TCC, KRD, and Director Secretariat, and I lack words for their participation and their willingness to complete tasks assigned in time. I personally thank my colleague, Sri R.D. Satish Kumar, Principal Technical Officer, for comparing, and Mrs. Lakshmi Purna, Senior Technical Officer, for event capturing of today's event. If I have missed out someone who have contributed directly or indirectly for the successful conductance of this event, it's not intentional, for which I may be excused. Once again, thank you everyone. Jai Hind.
Thank you, Professor. Thank you both of you. Thank you, Professor Sekhar and others who have joined. Dr. Nageshwar Iyer, if he is available, just he has left. Okay. Thank you, sir.
Thank you, sir.
Thank you very much. Thank you very much. It's a nice evening. Thank you. Namaskar, Professor Krishna.
With this, we conclude the event today.
Okay, we can leave. Thank you.